Hello you all. So, what we're looking at now is how we can apply some mechanical laws to describing how high a pole vaulter can jump to. So two things are going to be happening. The pole vaulter will run at a certain speed and will try to jump a certain height. So, and this is for you, Brian, it's all to do with energy. If a pole vaulter is running, they are going to have kinetic energy, half mass times velocity squared. If they're jumping and jumping high, they're going to have gravitational potential energy, which from now on I'm going to call GPE. So a GPE is equal to how massive the pole vaulter is times by the local strength of gravity times by the increase in height. Let's look at our units. We know that EK is joules. We know that gravitational potential energy is joules. We know we can make those equal to each other. Let's take a moment, think about why the units for GPE are joules. What's the unit for mass? Kilograms. What's the unit for gravity? Newtons per kilogram. What's the unit for height? Metres. So we've got kilograms times newtons per kilogram times metres. How can we simplify that? Get rid of the kilograms. So we're left with GPE being joules equal to newton metres. We know that works. Homogeneity of units, it's a cornerstone of physics. The units have got to be equal to each other. So we want to be able to predict how high our runner can jump depending on their kinetic energy. So if they're both joules, we should be able to combine the equations. So we can say m times g times delta h equals half m times v squared. We want to know how high they're going to jump. Let's make h the subject of our equation then. First thing that's going to happen, surprisingly, maybe not surprisingly, I don't know, our masses cancel out. We're going to come back to that later. Mass of the runner, the mass of the jumper, doesn't matter. So we're left with g times delta h equals half times v squared. So first thing we're going to do, move g to the other side. So delta h equals half v squared over g. No self-respecting physicist likes a bracket within a bracket. So we're going to move our half to the bottom of the bracket, and that becomes 2. So our increase in height is equal to v squared over 2g. And the mass of the athlete doesn't make the blindest bit of difference. Now, as far as I'm aware, all Olympic Games happen on Earth, so the only factor that affects how high they jump is their velocity. Now, if Usain Bolt is the fastest man on the planet, why isn't he also the person who can jump the highest? It's more than just running quickly. And this is kind of the engineering side of things rather than the pure physics. Delta H, where do we measure that from? Do we measure it from our head, middle of our body, from our feet? People who did P3 last year, did triple science, you'll remember we looked at the centre of mass of an object. That's going to come back into play now. For our athlete, their centre of mass is broadly about here, middle of your chest. So when we talk about delta H, we're talking about the change in height of the centre of mass. Now watch out for this in exam questions, so we'll try and slip you up by telling you the athlete is 2 metres high and his centre of mass is 1.5 metre. And I'll ask you to work out the delta H, and so you'll find out the delta H, but his peak height will be delta H plus this 1.5 metres because it was already off the ground. We're probably going to encounter that in our problems class on Monday. So why isn't Usain Bolt able to jump higher than anyone else in the world? It's all about the centre of mass. You'll notice when people do the pole vaulting, they don't jump like they do on, what's the terrible vampire film? Twilight. When they jump, they kind of just launch themselves forwards through the air. You don't see pole vaulters just launching themselves forwards. They bend and they twist over. Now the reason they twist is to make their centre of mass as low as possible, which means that their delta H gets larger because their centre of mass is lower. You're not trying to shift all of the body to that certain height, you just want to skip it over the bar. Having said that, so there's a lot of technique involved. Having said that, Usain Bolt probably could be a world-class pole vaulter because he is so fast. He'd have to train on how to do the twisting and be supple enough, but ultimately our equation shows us it's all about velocity. What I'd like you to do now is find the page, I don't have the page number wrote down, I'm sure you can find it. Find the page that's about pole vaulting. It'll be a bit further than the extension of a spring. I'd like you to try and do summary question 2. So pause me and try and do that. Okay, so hopefully you have succeeded. So we started off with delta H equals V squared over 2G. The question said he had a velocity of 10.5 metres, but metres per second, and we live on the Earth. Don't plug all those numbers into your calculator and push equals. You might not get it wrong today, at some point you will get it wrong, it will cost you marks. One step at a time. 10.5 squared is 110.25. 2 times 9.81 is 19.62. Divided by each other, they work out 5.62 metres. So the change in height of that pole vaulter changed the mass, centre of mass, will have gained a height of 5.62 metres. Or would it? Now with our bow and arrow, we never got our maximum velocity because some of this stored elastic energy was lost as heat and sound. It's the same here. Now the pole is almost perfect. When the pole stretches, you lose very, very little energy as heat. Our muscles aren't as good. When our pole vaulters at the top of their jump, their muscles will have heated up by insignificant by anyone else's calculations, but a reasonable amount. Enough to mean that this maximum height will never happen. The theoretical maximum assumes no energy is lost, but we know some energy always is lost. In this case, some is lost in the pole, but the majority, and I keep patting off camera, you can't see, but your thighs, the thighs will get quite hot. On page 128, I'd like you to try and do question 3, which is similar to this situation, but slightly different. You're going to have to use gravitational potential energy in a situation when things change their height, but it won't be exactly the same as the pole vaulter. Try that, bring it Monday, we'll see how you did. Thank you.